So a plane has taken off from the runway and gained a speed of 300 miles per hour, making an angle of 15 degrees with the horizontal. When the plane is 1,600 feet off the ground, a loose nut detaches from the plane and falls to the ground. Neglect air resistance and assume the plane travels on a straight line at constant speed. Approximate how high from its point of detachment will the nut rise. Okay, so first things first, we have 300 miles per hour, so we have to convert that to feet per second. So we know that 5,280 feet equals 1 mile. So we can go ahead and cancel out the miles, and now we have feet over hours. So from there, we have to get the hours to change to seconds. So we know that 1 hour equals 3,600 seconds, so we can cancel out the hours, and now we have feet over seconds. So after that, we finally have the units we wanted. So when we plug everything in, we get 440 feet per second. So now that we have the 440 feet per second, we can go ahead and look at what our problem's asking for. So we're trying to figure out how high the nut will rise from its detachment point. Looking at the graph or looking at a picture, we have the plane that's going at 15 degrees above the horizontal, and it's going at a speed of 440 feet per second. Now, the nut is going the same direction and the same speed, but eventually it's gonna stop going in that direction because of gravity, because gravity's pulling it down. Now, because of that, that causes a projectile motion type of problem where you see this arc shape. So from there, originally, we have the velocity vector in the y direction, and we have the velocity in the x direction. And because gravity is pulling the nut downward, this velocity in the y direction is going to start getting smaller and smaller. And eventually, we're going to have no velocity in the y direction, which is why we get a vector that's going just to the right.
And that is going to be the highest point of the nut.
Which is what we wanted. So how high will it rise? Now, just continuing on from that, after this point, gravity is going to start taking over, and then this vector is going to start moving downward. It's going to keep moving downward until it reaches the ground at some point. Okay, so now that we got that out of the way, we can go ahead and solve our problem. So we can solve it one of two ways. So our first one is going to be using the kinematic equation without time and just solving for delta x. And our second one is going to be solving for time first and then shoving that into this kinematic equation, which does have time. So let's go ahead and start off with the one without time. And before anything, we're only dealing with our y component for velocity. So we're going to go ahead and figure out what our y component is. So in order to do that, we know that the plane is angled at 15 degrees, meaning that the nut is also pointing 15 degrees away from the horizontal. So we're going to go ahead and do sine because opposite over hypotenuse. And we're going to go ahead and do 440 times sine of 15. And we get 113. 113.88 feet per second. Now, just a tip, make sure your calculator is going to be in degrees, and you should be good. So now we can solve for our delta x. we're going to have v2 squared minus v1 squared. We're going to divide that by 2a, and that's going to equal delta x. So now we're going to plug everything in. We know that v2 is going to be when the nut is going to be on the ground. That's going to be 0. So now we're going to have 0 minus 113.88 squared divided by 2 times negative 32.2. Now when we plug that into our calculator, we get 201.38. That's going to be feet, and that's going to be equal to our change in x. Okay, so now that we have this answer, we can go ahead and solve it using time. So we know that time equals the change in velocity over the change in acceleration. But one thing about time is when you're solving for time using this formula, that's gonna be when you're finding the time for the maximum height. So back to our airplane model, that's gonna be from this point to its highest point. So the distance from here to here. Okay. Now, when you want to find the distance from its initial point to its very final point, you're going to use this formula. And to solve it, you're going to use the quadratic formula. Okay. So we can go ahead and do the change in velocity equals v2 minus v1. And that equals 0. Since our final velocity is going to be on the ground, so it's not moving, we're going to subtract that by our 113.88. So we're just going to get 113.88 feet per second. And our acceleration isn't changing since it's constant, so we can just divide it by acceleration. So our time is going to equal to 113.88. Divide that by 32.2, and both of these are negative. So that's going to give us 3.54 seconds. Okay, so we got our time, right? So now all we got to do is just plug this into this kinematic equation. So we have our delta x equals our v1, which is 113.88. We're multiplying that by time, so 3.54 seconds. And then we're going to go ahead and add that to 1 over 2 times our negative 32.2 acceleration, and then multiplying that by our time, so 3.54 squared. So we have our v1, we have our time, we have our acceleration, and we have our time again. So when we plug that in, we get 201.38 feet. And that is this answer. So we solve it. Now going to a more precise calculation. Okay, so we have our velocity, and we went ahead and converted that into feet per second, and then we got our y value from the velocity. Now, this is our first equation that we use, and it's just rearranged. So we used this formula, and when rearranged, we get this. So we have our velocity initial, and we have our acceleration. Okay, so now we're solving for time. So we have our velocity and we have our acceleration. And we get 3.54. Now we have our second equation to solve it the second way. And when we plug it in, we get 201.38. And for the first equation, we get 201.38.